Okay, welcome back. So we're moving on to the next somewhat important PDE. This is the Laplace equation. You'll recall the Laplace equation is basically the second derivatives on the left-hand side. This is your Laplacian, hence Laplace equation. Second derivatives on the left-hand side added together, and then that's equal to 0. If I put a non-zero entry on the right-hand side, that's the Poisson equation. And let's just reduce it to one dimension right away, and then we'll maybe talk about some higher dimensions. So in one dimension, this actually becomes pretty trivial because how many second derivatives can you take in one dimension? Just one, and you take it twice. Two derivatives equals 0. We solve this just two integrals, right? So the u is the antiderivative of the antiderivative of 0 dx. Everybody's going to tell me that that's 0. You're wrong, because the inside one gives me a constant. It becomes 0 plus c. And the outside one gives me another constant, b. So actually, the solutions are the affine functions is how I'll call this. So these are the functions of lines in one dimension, cx plus d. Or, as your book likes to say it, ax plus b, right there. Ax plus b. So those are the solutions in one dimension. We'll talk about the solutions in higher dimensions in a bit, but let's just stick with one dimension for now, because just like with the heat equation, we have some constants that haven't been defined, a and b. So let's see how we can actually define them and gain something unique out of it. So suppose that we have some boundary conditions here. Remember, it's a PDE, so it's going to involve both initial and boundary conditions if we had derivatives in time and space, but in this case we only have derivatives of space. So we have u of 0 equals 0, u of 1 equals 0. Let's solve. So if I plug 0 in, I get u at 0 is a times 0 plus b equals 0. This is only true if b is equal to 0. Then u of 1 equals a plus 0, because b was 0, equals 0 only if a is 0. So it turns out in this particular case with these boundary conditions, what is the line that connects 0 to 0? The line is 0. So that's what we can think about in one dimension. Why is this actually useful? Way back, so this would have been like 2 lectures ago. I said something about, all the way back, wow, this is a long ways back. I said something about how the Laplace equation can be realized as a long-term behavior of the heat equation. So that if we let the heat equation equilibrate or go to infinity, then this equation reduces to solving this equation. And if I jump down here to the heat equation that we solved in the most recent lecture, we said that with those specific boundary conditions, the solution to the heat equation was right here, e to the negative pi squared t sine of pi x, and if I let t go to infinity so that this equilibrates, I end up with 0. u of x equals 0. You can kind of see the flat line that it ends at in positive time, so there's the u equals 0. So that's nice because we can really think about solving the Laplace equation as actually solving the heat equation and letting time tend to infinity. And we see that in the one-dimensional setting. And in fact, that's all the book actually introduces here. So there's one tiny thing I'm going to do now, because I want to give you a little bit more work than 4.5 minutes. So we'll head over to the whiteboard, and I'll talk a little bit about solving this in some higher dimensions. So here we are at the whiteboard. Let's grab the Laplace equation. Negative delta u equals 0. There's not really any reason for the negative to be there if it's equal to 0. I can put a negative sign on both sides. So I'm going to say delta u equals 0. Let's do this in 2 dimensions. 2 spatial dimensions. And let's do it on the square. So let's do it on the unit square, in fact. So I'm going to define this as my square. The xy plane. Call this omega. With there's 1 there, 0. And I'm going to give myself the standard boundary conditions, still Dirichlet boundary conditions. Sometimes we call boundary conditions, not because BC. Dirichlet boundary conditions would be u at, so if it's u of x comma y, u at 0 comma y equals u at 1 comma y equals 0. u at x comma 0 equals u at x comma 1 equals 0. So I'm going to give myself these boundary conditions, and I want to solve this in 2 dimensions. So how do I write the Laplacian in 2 dimensions? That's partial x squared, partial y squared, and we add them together. Get rid of those grid lines. Okay, so I'm going to do that same nonsense that we ran into with the heat equation, where I'm going to say assume, and I understand this seems like a strange assumption to make, but let's do it because it makes our life easy. Assume that u of x comma y is equal to f of x g of y. And when I make that assumption, then delta u, the Laplacian on u, is two derivatives in x, which gives me f double prime x, plus two derivatives in y gives me g double prime y. And if that's equal to 0, then I can go through the same song and dance as I did before and divide by f of x g of y. Okay, so let me do that. F of x g of y. What we get is we get a cancellation. If I'm just looking at that term, then the g's cancel. And if I'm just looking at these terms, because that division is distributing, right, then those cancel. And I'm left with f double prime of x over f of x plus g double prime of y over g of y equals 0. And then I need more space on my whiteboard, so I'm going to give myself some more space here. So this is the Laplace equation. Right there is the Laplace equation. If I make the assumption that u is a product of a function of x and a function of y. So if I make that assumption, this is an equivalent Laplace equation. And getting used to that same song and dance we did before, if I subtract g double prime of y over g of y from both sides, I don't want an equal sign there. I do that on both sides. And what do I recover? I recover that f double prime of x over f of x equals g double prime of y over g of y negative. And like I said before, the same song and dance says that if one side is only a function of x, one side's only a function of y, it means that both sides actually have to just be a constant. So I'm going to choose a negative constant again. In this case, I can't quite get away with the negative constant that I did the last time, the same way I did the last time. But we'll just do negative lambda, and we'll see what we get. So this, as before, this gives two ODEs. Right? If you want, you can jump back to the heat equation solution and see the process there. And the process is very similar. To extract the two ODEs, and the first ODE is f double prime of x over f of x is negative lambda. The second ODE is g double prime of y over g of y. And there's a negative sign from that. It's negative lambda. Solutions to the first ODE are, well, it's f double prime of x is negative lambda f of x. These are cosine and sine. C1 cos x, C2, so lambda, still lambda, root lambda x, C2 sine root lambda x. Give myself some more space. And the solutions to the second equation here, this is g double prime y equals lambda g y. I have g of x is c1 e to the root lambda y plus c, I should call this the c3, c4 e to the negative root lambda y. The reasons why one of them ends up as cosine, one of them ends up as e, is because we decided to put the negative sign there. If I had flipped that and gone with positive lambda, the cosines and e's would have swapped. And there's a complex analysis reason for that. It comes down to Euler's identity. But we won't worry too much about it now. This is perfectly valid for us. And so our final solutions are of the form u of xy, which was f of x times g of y. If I actually multiply f of x and g of y together, what do I get? I get all combinations of these. So I really get c1 e to the root lambda y cosine root lambda x. That's lambda x, oh, kitty cat, plus c2 e to the negative root lambda y sine lambda x plus c3, and I'm relabeling the c's, okay, so the c's up above are not the same c's down below. I'm relabeling them so that they're on each term separately. E to the minus root lambda y cosine root lambda x plus c4 e to the, okay, I put a negative there for some reason, so this is positive root lambda y sine root lambda x. And there you go. We have solved the Laplace equation in 2 dimensions, but I have not solved the Dirichlet boundary conditions yet, okay? So plugging the Dirichlet boundary conditions in here, that's going to give me some values for C1, C2, C3, C4, as well as lambda. And I would solve that for you, but it turns out the C1, C2, C3, and C4 and lambda, they're not that pretty. So we can talk about it in class if you want to, but just trust that you can do it because it's a system of 4 unknowns and 4 equations, and then lambda actually sticks along for the ride. Anyway, that's all I have for you. I'll see you in class. Bye.